Hello, my name is Aaron Sigman, and my project for this remote sensing class is identifying land cover changes over time in South Suburban Denver, Colorado, using Landsat imagery. A little bit of background on land cover. Urban and suburban remote sensing specifically can play many roles in understanding the distribution of land uses, land covers. For growing suburban areas, much like this one in the South Denver area, regions can be monitored for a variety of different things, including tracking residential development, water reservoir storage capacity, and changes in commercial and open space areas. This monitoring is important for a multitude of reasons, including but not limited to residential zoning, commercial development, tax assessments, transportation, parks and recreation, emergency management, and further real estate development. We can see in this plot that the Denver metro area has grown fairly rapidly from approximately 500,000 people in 1950 to about 3 million people today. The objectives of my project were to compare land covers over time. This initially started by comparing the known National Land Cover Database datasets, or NLCD, over a 3-year period, 2016 to 2019. And then I wanted to access more years worth of imagery from Landsat 8 and classify those images for land use. This would also allow the comparison between NLCD's changes and the classified changes that I make, and I would be able to note regions of major change and development. For the study area of this research, I have chosen a suburban region in the South Denver metro area. This includes a large number of already developed neighborhoods, regions of current development, and open spaces and state parks. A large portion of this region has been undergoing a large residential development in the last 10 years, and we should be able to see that in this work. This study area was limited to a circle with a radius of about 14 kilometers, or an area of about 615 kilometers squared. There were two methods to this research, the NLCD side and the Landsat side. For NLCD, the data just needs to be imported, clipped to the study area, and reclassified. This involved reducing many of the land cover classes to just 4 to make things simpler. We went with water, urban, vegetation, and then shrubland/bare soil. By doing this for both years, we can compare the changes over time. For Landsat images, there are more years to pick from, and I decided to go with the maximum range of data available from Landsat 2013 to 2022, with a year in the middle for 2018. To try and minimize variability between the images, I picked an image for each year that was in the summer and had the least amount of cloud cover. This allowed for the creation of multiple images, true color, false color, and NDVI, utilizing the different bands of Landsat 8 to visualize the study area. Using these created images, I selected regions within the study area to classify for each desired land cover, and ran a classification and regression tree. This resulted in the creation of a land cover map for each of the year's images. Here are the NLCD datasets plotted for 2016 and 2019. We can see that up north we have much of the existing development in neighborhoods that have been around for many years. There are also a number of reservoirs and rivers throughout the images. Much of the southern region is mainly shrubland or grassland, but we can see some of this is going away in newer development communities just south of the main reservoir and along the highways that run north to south. By reclassifying these into simpler categories, urban, water, forest, and shrubland, we can compare the year's changes from 2016 to 2019. By doing this, we can see an increase of about 1.2% in urban and a decrease of about 1.4% in shrubland, with water and forest having slight increases. Moving on to Landsat Imagery, we can visualize the changes from 2013 to 2022. One thing we can pick out changing between these years is the changing of vegetation or the general color palette of the image. Where 2013 was a much wetter summer, has a bit more green in it, and 2018 and 2022 were a little bit drier. We can also begin to see the new development that shows up south of the reservoir here and alongside the rivers running north and south, and then along the highways as well. In the false color images, this change is again noticeable between the years, but we can more easily pick out the regions where development is beginning to occur. South of the reservoir, there are new bright spots that indicate some of the new development progress, where many of the foundations are being laid for housing that is going up. For NDVI, we can see these differences again in vegetation, mainly due to climatic differences and wetness between the years. But again, we can also see those changes in the same regions of new development beginning to occur in those deeper reds and brighter colors. After looking at these images, I went through for each year and picked out regions for classifying land cover. Red being urban, green being vegetation, yellow being the shrubland, grassland, or soil, and blue being water. With this, ignoring some of the noise in the classification, we can now more easily tell these regions of development. This also allows us to pick out some of the roads more easily that travel between regions, as well as a lot of the new developments that are popping up. In a bar plot, we can see the changes of Landsat classified covers over time. Blue shows the percent changes from 2013 to 2018, orange from 2018 to 2022, green being the total change from 2013 to 2022. The amount of water stays about the same like we saw in the NLCD land cover, but we also see an overall decrease in both forest and shrubland. Then there is a large increase in urban development that follows with the decrease in forest and shrubland. There are a number of limitations to this project, first being the 30-meter resolution of the Landsat data. This means we may not accurately capture the smaller transitions between some of the land cover types, as well as maybe overclassifying some due to this overlap. Second, the comparison between NLCD and Landsat are going to differ for multiple reasons. We have differences in the years used, and with that comes changes in the climatic conditions, i.e. the wetness or vegetation amounts that we can see in those images. Also, the categories between NLCD and Landsat may be differ. I simplified the 15 NLCD categories that were in this region to just the 4, possibly limiting the accuracy of the information. For the Landsat, especially at this resolution, it can be difficult to compare grassland to vegetation, as these regions may be overlapping or producing different returns based on the water content year to year. This means that the direct comparison of vegetation to soils between the two classifications may not be the most accurate, but it should still be capable of showing the trends. Lastly, I wanted to do a bigger study area, but was limited to the processing capabilities of HydroShare's notebooks. In conclusion, this initial pass at classifying multiple years of land cover does a decent job of identifying regions of change and the general trending changes. We are able to identify the amount of development seen over the past 10 years, but this method does have its limitations. Thank you, and this code will be available on my GitHub and will also be published as a HydroShare resource soon.